To finish up our last portion of Chapter 7 work, we need to talk about one final concept, and that's power. We'll define power in the world of physics as the rate at which work is done. So in other words, if we know how much work is being done by forces, conservative and non-conservative forces, and we divide that by the amount of time that it takes to complete the work, that gives us our component of power. So an example that I like to give here is somebody turning a wrench and somebody else using an impact gun. If I'm trying to take the lug nuts off of the wheel of a car, if you've got a regular wrench, you can get it done. You can complete the job. You can do the work. But if you were to come in here with an impact wrench, something that's mechanical or electrically driven or pneumatically driven, you can remove the nuts and change the tire much quicker. So as the time that it takes to complete a job or to do an amount of work goes up, then the total amount of power that you have is decreased. And the opposite is true. If it takes you less time to complete an object or a task, then you're actually producing more power. There's an inverse relationship between time and power. So, in keeping with the theme of interesting units and dimensional analysis, if we know that work is a measurement of joules and time is a measurement of seconds, we now have a unit for power known as a joule per second. And that's all well and good, but we are now seeing here that we're going to introduce a new computed unit called the watt to represent that. So this can be a little bit confusing if we're using W for work, especially if we use capital W for work, and we're now using capital W for watt. We should use capital W for watt because that is a person's last name. So use a capital W for watt there. The notation can be a little bit confusing. Now, another common unit of power that we sometimes see is a horsepower, and I don't exactly know where this conversion came from, but 1 horsepower is equivalent to 746 watts. And when we start talking about electricity, you'll also see kilowatt hours or just plain watt hours as a unit of measure. Now here again, if a watt is a joules per second, and if hours were converted into seconds, then we'd have our units canceling here and we'd be back to joules. So even though we are talking about a unit called a watt hour or a kilowatt hour or a watt second, if we're talking about a unit like that, we're not talking about power, we're actually talking about energy. So that's kind of an interesting comment here. So our textbook likes to go through a couple examples, and our notes from the university like to go through a few examples here. Starting to be a little bit dated in this reference, but still true for the time being. Aaron Rodgers can accelerate a football that has a mass of 0.43 kilograms from rest to a speed of about 60 miles an hour in about a fifth of a second, 0.2 seconds. During the throw, what is his average power output? Well, right off the bat, we've got to convert miles per hour into meters per second so that all of our math works well without additional conversions. The formulas that we have are all built on SI units. So we have miles per hour. If we go through a T-chart or a picket fence or any number of ways to convert, appears to be 26.8 meters per second. Then if we discuss power as the quantity of work done over time, work in this case is our change in kinetic energy. And we've seen that in a prior discussion when we were talking about those PBL activities from earlier. So we have a few different notes here that the network that's being done is the change in kinetic energy, and we've seen that show up a couple other different places as well. So if our work is the change in kinetic energy, since the object had no velocity at the beginning, it was at rest, then the change in kinetic energy is the final kinetic energy minus 0, or just the final kinetic energy, which we know the final kinetic energy to be half mass velocity squared. The textbook chose to move the 1/2 that was in the numerator and split that into numerator and the denominator of the existing fraction. So there's our 1/2. It is accounted for. mass velocity squared, substituted quantities. It looks like the computer result ends up being 773 watts, or about 1 horsepower in that throw. So that's kind of interesting. Lots of power, we can say, in the arm of an NFL quarterback. And then the final example that we see in the notes, or in the summary notes here, is asking us to find the cost of running a computer that draws 650 watts of power, or watts of energy, I should say. Well, no, power. Let's be consistent here. A watt is a measure of energy per unit of time. So requires 650 watts of power to operate, and it's going to operate 6 hours a day, 30 days, and the cost of electricity is 12 cents per kilowatt hour. Okay, so we have lots of conversions that have to be done here. Watt is the SI unit of measure for power. However, the cost of electricity was in kilowatt hours, so it looks like that the textbook liked to convert 650 watts straight into kilowatts right off the bat. Now, if we have our kilowatt unit, which remember is a measure of power, power is a joule per second quantity, or in this case, kilojoule per second, we would need to multiply by some time component in order to get energy. In this case, kilojoules, but there would be some conversions to get us into hours as well. We need to get into a unit of energy so that we can determine the cost for running this computer, because energy is sold in well, electric energy is sold in energy units, a kilowatt hour. So a T-chart would work. The textbook didn't choose to set up a T-chart this time, but all of the units will work out. Kilowatts times hours divided by days multiplied by days. So this is kind of an interesting, this multiplication of 30 days is not part of a unit conversion, but it's just a multiplication here. So the day units will cancel. The product of these numbers does come out to be 117 kilowatt with the hour unit, since the day is canceled. So kilowatt hours is how much is being consumed. And so the cost would be 117 kilowatt hours times 12 cents per kilowatt hour. The kilowatt and hours units will then cancel, and we're left with our money unit, $14. So evidently, if you're running a computer 6 hours a day for approximately 1 month, you're going to be charged around $14 just to operate that computer. So that brings chapter 7 to a close. If we were to jump over and look at the homework questions, I think the problems are remarkably similar to what we just discussed here. So you can use them as reference while completing your homework number 9 and 10. If you have further questions, please reach out to me. I'll be happy to chat with you about them and try to make them make more sense. And for most of you, I will see in class tomorrow for lab number 7. Thanks a lot for watching.